these are my equations, right? And my question is, can you come up with a matrix A such that this is equivalent to saying some, y alpha less than equal to 0? Right? So this is equivalent to y minus alpha correct? Now with this description you can come up with A. Is that okay with everyone? What is A? Minus identity. Right? So this multiplied by less than, right? First equation will be minus y plus x alpha less than equal to 0. Second equation will be y times identity minus x alpha less than equal to 0. And sounds good? Great. So we are almost there, right? We have this inequalities with 0 on the RHS, but with more variables than we want, right? So how should we, so we need to remove alphas. How can we remove alphas? No, but then you will lose. Like what you want is you remove doesn't mean just erase. Remove means you have to come up with an equivalent system so that a solution there is a solution here and the solution here is a solution there, right? So you want to show that they are equivalent. So this is done by something called Fourier-Motzkin elimination. This is a nice trick, works in generality, and you can probably come up with it if I hadn't told you already, right? So what does it do? So let's say we have this system Ax less than equal to b, where you have m inequalities and n variables. Okay. Fourier-Motzkin elimination changes it to b prime, where now you have n minus 1 variables and x prime is, you can say, x1, x2 up to xn minus 1. So it's the first n minus 1 variables of x, and you incur only small overhead in terms of number of inequalities. Okay. And then the point is, so this is, let's say, the old system, this is the new system. Then if you have x, which is a solution of old system, you break it down into x0 comma y, x0 will be a solution of new system. And if you have a solution for the new system, there exists y such that x0 comma y is a solution of old system. Okay. This is what we are going to So if you believe in Fourier-Motzkin elimination, do you agree that a finitely generated cone will be defined like this, ay less than equal to 0? That is easy to show. No, like I mean, a finitely, it's a convex cone that you can show. Ax less than equal to 0 set, which is ax less than equal to 0, is a convex cone. That's not hard to show, right? Now the question is, given a convex cone, can you convert here, right? So now we are here. My question is, assuming Fourier-Motzkin elimination, are we okay? Done? We can get to ay less than equal to 0? No, you are asleep. Sorry? So, but yes, you are missing something. So wake up. Tell me what you are missing. Exactly. In this case, we have to make sure that if we start with 0, we end up with 0. Right? This is not clear from this definition of Fourier-Motzkin elimination. Okay? So I'm going to tell you how Fourier-Motzkin elimination works, and you have to make sure that it keeps this right hand side being 0 property true. And then we are sure that we can convert any ax less than equal to 0, y alpha greater than equal to less than equal to 0 to some a prime y less than equal to 0. Okay, and then we will have a nice characterization of the cone, convex cone. Sounds good? Okay. So any ideas? How should we eliminate? You have a variable. So okay, let me help. There are three kind of inequalities, right? Everything is of the kind ax less than equal to b. There are three kind of inequalities p, where coefficient of xn is positive, n where it is negative, and z where it is 0. Right? Three chances. Which one is easy to take care of? Right? What should we do about this? The coefficient of x, in this set of inequalities, the coefficient of xn is 0. So it doesn't depend on xn. So it's already removed. It is already of this form. So if I look at all the inequalities, no. I am dividing my set of inequalities into three parts. So my total set of inequalities are inequalities here, plus inequalities here, plus inequalities here. Right? So obviously this inequalities I will just carry forward. I will put it in my new system directly. What should I do with this? Okay. So what we will do is, for every I element of P and j element of n, we will introduce the inequality less than equal to 0 with a small change, which is you take the inequality here and make so that the coefficient of xn is plus 1. Here you can divide the coefficients so that the coefficient of xn is minus 1, right? So then here when I do this, my xn is gone. If my solution satisfies these two, does it satisfy this? Yes. I can do this. Now this is my original pi. This, right? Oh, okay, sorry. If I am considering pi in the old system, then clearly pi is less than equal to 0, nj is less than equal to 0, so their sum is also less than equal to 0. So this I get for free. This was the easy direction. What is difficult? If this is true, then can I come up with this? no inequalities of second kind. Think about it, that's a very easy case. You will have, like, you will just keep pi less than equal to 0 and you can satisfy it for free by keeping x0. Remember that the coefficient of x0 is the same everywhere and your x0 is unconstrained. So there is a choice of x0 which will trivially satisfy all this. If in all your inequalities x0 appears as positive, you can take x0 to be minus infinity and all the things will be satisfied, right? You are saying that you only have inequalities of this form, right? So you have only inequalities of plus x0 less than equal to 0, plus x0 less than equal to 0. So this I can trivially satisfy. I will just put x0 to be minus infinity or something, right? Big thing. And if it is all minus minus x0, I will take x0 as positive infinity. So then these things will be automatically satisfied. So I don't have to worry about it. So what do we want to show? We want to show that if I have a solution y, or what did I call it? I call it x naught, right? System, there exists a y. I want to fix my final variable such that my old system is satisfied, yes. Comma y is a solution of my old system. Sounds good? Okay. So let's say, okay, with abuse of notation, now I will say now pi are my inequalities in the new system where your x0 is kind of removed. You can call them pi prime if you want, but this is, what did I call it? Define it to be pi. And sorry, this should be the other direction. So pi is defined as the value at y of this inequality. Similarly, right? So look at the old inequality, right? Remove xn from it. So I'm abusing notation, I'm also calling that pi. So pi y is some value.
Is it coming from the new set of inequalities?
Yes, yes. Sorry. Sorry.
X0, we eliminated X0.
We are eliminating xn. x0 is the solution of the new set of inequalities, right? So I am writing pi x0 as pi and I x0 as ni. So basically whatever are the values, right? So what I want is for all I element of p, j element of n, I know that pi plus nj is less than equal to 0, right? This I know, and now I want to come up with a y. And then what should happen is I want to come up with a y such that y plus pi is less than equal to 0. So what does this mean? What does this equations mean? This is for all I. So this means y should be less than min of minus pi. This says pi, these are numbers. No, y is just one value, right? It is xn. What are we doing? We have new solution. We want to show so that x naught y is the solution of old. So y is the value of xn. We just want to set one variable, right? Good. So now, why is this feasible? Because of this. Right? What is this saying? Any minus pi is bigger than any nj. That means the minimum here is going to be bigger or at equal to the maximum here. So the feasibility is implied by, and the way we constructed it, we made sure that RHS always remains 0. We did not have any non-trivial constant variable, right? So this shows Weyl's theorem, which is that a finitely generated cone is specified by equations Ax less than equal to 0. Okay? And now we can make a very nice table. Depending on the kind of person you are, you might like this column or this column. But for this course, you need to like both the columns. Okay, so what do we know about affine subspace? It's a shifted linear or vector subspace. And in terms of equation, it is written by this. I can just write less than equal to b because greater than equal to is covered. Correct? This is we defined it like this, and now knowing we have the definition of cone, it is basically convex hull of cone of Z1 to Z10. Okay. What does plus mean here? Take an element here, take an element here. Okay. So this is called Minkowski sum. Simply put, S1 plus S2 is you take element of any element of S1, add it to an element of S2. Okay. This I will not prove. This is Minkowski-Weyl theorem, which is outside the scope. Okay. Okay. Then you have polygon which was bounded polytope, right? So this is convex hull of x1 to xn. Clearly it is bounded, it can't have this. And if it does not have this, then it has become this. So if you assume this line, this is Minkowski-Weyl, then this follows. Okay? And what is the last one? Convex cone. Finitely generated cone. Convex cone is slightly more general. You can have this ice cream cone, right, which is completely circular. That would not be finitely generated, right? So for what we are interested in, finitely generated cone, which is cone of y1 to yk, this is ax less than. So for the course, the important thing is understanding these shapes and their equivalent transformation. The proofs are not important, I just covered one so that you at least have a flavor of how convexity and all these arguments are used.
Finally generated cones are polytope, right?
Oh, they are obviously, because this is of this kind. Yes. So this is a subset of this. Yes. And this is a subset of this.